Hello, dear students. Welcome to the channel and very welcome to this playlist in which we are discussing about symmetrical and unsymmetrical faults and symmetrical components. We have already covered the symmetrical faults section, so today we are going to begin with symmetrical components here. So, if you haven't checked out previous videos in which we have if you haven't checked out the previous videos in which we have discussed about the symmetrical faults, please feel free to check it out. The link will be on the top right hand side corner of your screen on the I button, so you can click on it and you can check it out. So now moving forward to the symmetrical components. So first and foremost question, that what is a symmetrical component? How do you identify a symmetrical component? What is it, right? So, to understand the symmetrical fault, let me take you back to most of the common faults which occur in the power systems. So, if you are living in any urban city or even if in a rural area, you must have heard about or seen the faults called as ground faults or line to line faults or line to ground faults, because those faults are the most commonly occurring faults in my power systems, right? And uh, these faults, line to ground fault, line to line fault, such faults are called unsymmetrical faults, because whenever such fault will occur, your system will become unbalanced. Okay, so because of that we call it unsymmetrical faults. And under this condition, the unbalanced condition, the analysis is done on three phase basis. Okay, so there is a more convenient method which we can use for analysis of unbalanced faults, and we call that method symmetrical component method. And now coming to the symmetrical component, what is symmetrical component? So what do we do in the method which I just discussed, the symmetrical component method? In that method, uh, the three phase unbalanced voltage and currents are transformed into three different sets of balanced voltages and currents, and we call it symmetrical components. We call those components symmetrical components. And by using this method we can resolve any any problem related to unbalanced system. So we can resolve unbalanced system of impedances into three equivalent single phase systems with independent value of impedances. The three independent impedance systems can be suitably connected to represent all type of fault conditions, not limited to any one particular, but we can use it for the all type of fault conditions. Now you must have a question that where do we use such symmetrical components, right? What is its application? Okay, now you know what is basically a symmetrical component. Now you want to know what is the application of it. So firstly, the symmetrical component method, what it will do, it will convert your three phase unbalanced three phases into independent sources, right? So whenever you have a three unbalanced phases, and whenever you apply symmetrical components, what will happen, it will convert your three unbalanced phases into three independent sources, and these three independent sources will simplify a symmetrical fault analysis, right? Using these three unbalanced phases, we can simplify the calculations of asymmetrical fault analysis. And how can we do it, we will see it as we move forward with the chapter, because we are also about to see the line to ground and line to line faults in detail, so we will see this as well. The other advantage of these systems are like symmetrical systems or symmetrical components expand one line diagram or single line diagram to show either the positive, negative, or zero sequences. Basically, there are three type of sequences called zero sequence, positive sequence, and negative sequence. Don't worry, we will see all of them in detail as well. Today only we will see them and we will understand it. So, what it does, this zero sequence, positive sequence, and negative sequence impedances, and you can find it for anything. You can find it for transformer, you can find it for generator, you can find it for transmission lines. Okay, so you can find this zero for positive and negative components for anything you like. It must be just electrical system, right? And what it will do, this components, they will simplify the analysis of unbalanced condition, right? And which unbalanced condition? So the fault we just mentioned in the beginning of the lecture, the line to ground fault, line to line fault, right? Such faults are your unbalanced condition faults or unbalanced faults. So we use them in order to deal with that. And there is third and foremost important point related to this, that what happens in three phase winding. Physically, we normally use positive sequence as the current produces and normal rotating field will be generated. We use the positive sequence, but what will negative sequence will do? Negative sequence will produce field with opposite rotation. Okay, so in positive sequence, if you are going clockwise, so in negative, you will go anti-clockwise and vice versa. Okay, and then we have the zeroth sequence, which is a little interesting. It will produce a field that oscillates but will not rotate. Okay, so this effect, all three of these effects can be detected physically with sequence filters. There are filters called sequence filters, and if you want to detect either if your what is the symmetrical component of your system, you can identify with the help of these sequence filters. So we use it to detect physically your sequence, if either it is positive, negative, or zero, and based on that you can detect the fault and then you can do the remedy. So it will become the basis for design of your protective relays, right? And we use them with negative sequence voltage and current as a reliable indicator of the fault conditions, right? What does relay does? Relay indicates whenever fault occurs, right? So now let's see each of the sequences one by one. So any symmetrical component, whatever you take, can be expressed in phase sequences, and that is what exactly we are going to do. The order in which this phase quantities go through the order, uh, whichever order you take in which these quantities will go through a maximum, in that order you will arrange your symmetrical components. Okay, and uh, there are three types of these sequences. The first one on the immediate left, which you are seeing, the figure I, that is called the positive phase sequence. So here you can see three vectors, IR1, IY1, and IB1. So initially I took the current vectors, but you can also take the voltage vector as well. So there is no issue, you can take either current or either voltage vectors, and based on that you can identify or you can calculate further fault calculations. So firstly you will take IR1, IY1, and IB1 as your current vectors. As you can see in the image, they are holding equal amplitude, and the phase difference between them is 120 degree. So phase difference between IR1 and IB1 is 120 degree. Phase difference between IY1 and IB1 is also 120 degrees, and phase difference between IR1 and IY1 is also 120 degrees. Now the phase difference between IR, uh, but 120 degrees, but in negative. Okay, IR1 and IY1 is having phase difference 120 degrees, but in negative, which means either you can take minus 120 degrees or you can take 240 degrees as you are moving in anti-clockwise direction for calculation of phase angles, right? So formally, you can say that in this phase sequence, the phase or line current or voltage, whatever you take, in this case we are taking current. So the line current will sustain maximum in the same cyclic order as in the normal supply system. So what we will do, we will assume the conventional clockwise rotation here. So R will come first, Y will come second, and B will come third. So this way it will complete the RYB in the clockwise rotation manner. Now there is something interesting which also we are going to discuss about. Any balanced system corresponding to normal condition will contain a positive phase sequence only. So if you want to detect if your phase sequence is correct or not, or basically if you want to confirm if the condition of your three phase system is correct or not, so what you will do, you will just check the phase sequence. If it is correct, if they are all of them are placed 120 degree above or far from each other, then they are okay, and your system is in the normal condition. So we have three phases of this sequence, and they are holding equal magnitude and spaced 120 degree apart. So based on that fact, these phasors can be represented as a1, a2, a1, b1 and c1. And you can write a1, b1 and c1 in this manner. You can see a1 will be a1, b1 can be given as b1 is equals to a1 angle minus 120 degree. See, if you take this a, b and c, then a1 is minus 120, b1 is minus 120 degree a1, right? So you can represent this minus 120 degree with e raised to minus j 2 pi by 3 as well, which is also called alpha square, which is a operator or a constant. And we are going to see in detail about alpha as we move forward, so I'm not explaining it here. I will explain it today only, but no issue. Then we have the third component, C component. It is 120 degree far from A1, as you can see here. We call this one A, this one B, and this one C. So A and C are 120 degree apart from each other, same magnitude. So C1 is equals to A1 angle 120 degree. And same ways we did for B1, we can write for C1 as well. A1 e raised to j 2 pi by 3. Here we wrote e minus j 2 pi by 3 because we had angle minus 120 degree, right? Here we are having you can say you can also call minus 120 degree is equals to 240 degree as well, right? So the equation will remain same for 240 degrees as well. But for positive 120 degrees, what will happen? You will have a1 e raised to uh, j 2 pi by 3 or alpha into a1. So that was your positive phase sequence. Now let's see negative phase sequence. Okay, so here you can see in the middle one, the figure 2, it is indicating your negative phase sequence. And what will happen in the negative phase sequence, this IR will be here ib will here and iy will be here. So instead of ryb you will be having rby. Or if you just want to remember it in a better way, so what you can do, you can remember that it is going counterclockwise. See, it is still ryb, but it is in counterclockwise ryb. See, first r, then y, then b. So it is still ryb, but it is in counterclockwise, totally opposite to positive sequence, right? And that is the reason why it is called negative sequence. So when the rotation will be counterclockwise, what will happen? The angle between r, uh, r and y will become 120 degrees. Here the angle between r and y was minus 120 degrees or 240 degrees. But in negative sequence, the angle between r and y will become 120 degrees. Same way as the angle between y and b will be 120 degrees again. Angle between y and b was 120. Angle between r and b will be again 120. So angle between r and b is still 120. But the angle between uh, yeah, okay, that's all the angles we took care of all the angles, right? So if you are going clockwise, r1 y1 and b1 ryb, if you are taking that clockwise is positive sequence. If you are going anti-clockwise, ryb, that is negative sequence, right? And no more major differences here, but only the difference of sign will be there. Okay, so same you can say, you can see here phasors will rotate in the anti-clockwise direction but will attain same maximum value in reverse order. Like what will be the reverse order? So acb or rby, right? And this sequence will arise under unbalanced condition whenever unsymmetrical fault is occurring. So if unsymmetrical fault is occurring, then your unbalanced conditions will be there. Unbalanced condition will be there, so you will be having negative phase sequence, right? So whenever you check for your phase sequence and it is negative, which means there is a possibility that unsymmetrical fault has been occurred in your system. So again here as well, this three phasors will be negative phasors, and they are sequenced apart from each other with 120 degree, and the magnitude will be equal in all three of the phasors. And we can call it a2, b2 and c2. So see this lower image, b2 can be represented is equals to a2 120 degrees, same a2, b2 and c2. So this is a and this is b, so angle between them is 120 degrees. So b2 is equals to a2 120 degrees, can also be represented same ways, a2 e raised to j 2 pi by 3, same way we represented here as well, is equals to alpha into a2. Forget this 5, it is a2. Okay, same ways you can represent it with the help of c2, and c2 will be equal to a2 angle 120 degrees minus, but see, it is 240 degree apart from it or minus 120 degree apart from it. So c2 will be equal to a2 angle minus 120 degree, and a2 minus 120 degree will be equal to a2 into e raised to minus j 2 pi divided by 3, same as this condition, will be equal to alpha square into a2. So remember, did you noticed one pattern here? Whenever you have a negative sign here, you are getting alpha square, and whenever there is no negative sign, you are only getting alpha here. So we will be going in the depth of it whenever we finish the zeroth sequence, because zeroth sequence is still remaining. So first let's discuss zeroth sequence, and then let's go to the operator thing. So the third image you are saying in your immediate right is zeroth sequence. And see, all three of your vectors ir0, iy0 and ib0 are in same phase here. They are not 120 degree apart from each other or not any degree apart from each other, but they are in same phase. So a phasor system combining three equal phasors in the same phase is known as zeroth phase sequence. Okay, and what does it represent? So these represent the residual current or voltages. Your system can have some amount of residual current or voltage present in it. So it will represent the residual current or voltages present under fault conditions on three phase system with or three turn present over there. So it will represent the fault condition to to the ground. And if you see the presence of zero phase sequence, what does it indicates? It indicates that uh, when fault to earth current can return to a system via star point of that system, right? So it represents the fault condition to ground, and its presence will arise only when the fault to earth current can return to system via star point of the system. And we represent zeroth sequence by IR0, Y by 0, IR0, IY0 and IB0, or you can call it A0, B0 and C0 as well. So some books will follow the RYB terminology, some books will follow ABC terminology, so you are free to pick whatever terminology you want to pick. In the end, the meaning should not be changed, meaning should remain as it is. Okay, now let's come to operator, which I promised to discuss. So the complex number which we saw after the angle is the operator, and it is defined at alpha is equals to j into 120 degrees. And if you want to represent that degree in radians, so you can represent 120 in 2 pi by 3, because we represent 360 degree by 2 pi, right? So 120 will be the third part of 360, so you can represent it by 2 pi by 3. So now multiplication of phasor by alpha or e raised to j 120 degree will turn it through 120 degree in counterclockwise direction. So you want a phasor uh, in counterclockwise 120 degrees, you can multiply your phasor with alpha. And whenever you multiply your phasor by alpha square or e raised to minus j 120 degree, it will turn your phasor through 240 degrees in counterclockwise direction, or you can say minus 120 degree in clockwise direction. So the operator's properties have been given here. Rather than calling properties of operator, I will call them the representation techniques of operator. You can represent it in polar form, or you can represent it in complex form. So here they have represented it in an exponential form first. So alpha is equals to j 2 pi by 3, or you can also write it as 0.5 plus j 0.866. Just converted my exponential term into complex numbers. Alpha square, which was e raised to minus j 2 pi by 3, you can represent it in the same way. This time the only difference will be the sign before the complex number. The imaginary number will be changed. So the value will be minus zero point 0.5 minus j 0.866. And whenever you take the alpha square, remember I've told you that alpha is 120 degree apart, alpha square is 240 degree apart. That means alpha cube is 360 degree apart. And whenever something is 360 degree apart, it means it is 0 degree apart. It is equal, 360 and 0 are equal, right? So you can write alpha cube is equals to e raised to j 0, and anything raised to 0 will be 1. So alpha cube will be 1 plus j 0. And interesting fact is, whenever you take the summation of alpha plus alpha square plus 1, it will always be 0. Why? Because all three phases are 120 degree apart from each other, and their magnitude is equal, which provides the balance to your system. And because of that, the alpha plus alpha square plus 1 will always be 0. Now let's come and discuss some symmetrical components of unsymmetrical phasors. So let's consider some of the phasors. So let's take VA, VB and VC as the set of three balanced voltages, and it will be characterized by equal magnitude and phase difference by 120 degrees, ideally what we did. And the set is said to have positive phase sequence, which means VB will lag VA by 120 degree and VC will lag VA by minus 120 degrees or 240 degrees, you can say. So you can represent the three phase all three phasors with in terms of VA. So VA will be VA itself, VB will be alpha square into VA. Remember VB was where did it go? Remember, if you are taking R Y B, it said they said positive sequence, so you are taking R Y B. So between R and B is 120 degrees, but between R and Y is 240 degrees, right? So here what will happen, the VA will be VA, VB will be alpha square VA, VB will be alpha square VA. I'm showing it again to you. This is A, this is B and this is C. Sorry, A, B and C, this is positive sequence, sorry. R, Y, B, this is A, B and C. So it means it is starting from here and completing its cycle in clockwise manner, and the angle between this and this is 120, but this and this is 240. So that's what they have indicated over here. So you can take VA is equals to VA, you can take VB is equals to alpha square into VA, and you can take VC is equals to alpha into VA. Same ways if you want to find for negative phase sequence, which means for this sequence, can you tell me what will happen? RYB is your ABC, this is your A, this is your B and this is your C. So angle between R2 and Y2 is 120 degree, but angle between R2 and B2 will be 240 degrees. So considering them is RYB, VA will remain VA, VB will become alpha into VA because it is directly in contact, it is 120 degree apart from VA, and VC this time, which is 240 degree apart from VA, this VC will become alpha square into VA. So the positive phase sequence can be marked by subscript 1, negative can be marked by 2 and 0 can be marked by 3, just for our convenience. And then what we can do, we can find the set of balanced positive sequence phasor for each of sequences positive, negative and zeroth. So first let's find for positive, VA1 and VB1 will be equal to alpha square VA1 and VC1 will be equal to alpha into VA1, right? So VA1 will remain as it is, VB2 will be alpha square VA1 and VC1 is equals to alpha VA1. Same ways for negative sequence, VA2 will remain as it is, VB2 will become alpha into VA2 and VC2 will become alpha square into VA2. And for zeroth sequence, because we already know that all three vectors are holding same magnitude and same angle, so it doesn't matter which analogy you use, you can call it VA0 or you can call it VB0 or you can call it VC0, all three are same, so we collectively call them VA0. Okay, so when I say VA0, that also means VB0 and VC0 as well. So now let's consider set of three unbalanced voltage VA, VB and VC, and then we will apply the Fortius theorem to three phasors. By the way, if you are trying to remember what was the Fortius, who was Fortius, so he was the American guy who suggested this phase sequences, zero phase sequence, positive and negative phase sequence. So he was the person who suggested it back in 1918, more than 100 years from now on. precisely 104 years, so too long time ago. So the addition of symmetrical components to generate VA, VB and VC, we can see it in this figure. Okay, so here you can see this is my VA1, this is my VB1 and this is my VC1, and we wrote the way to indicate them here. So VA will be VA1 plus VA2 plus VA0. So we are trying to find the ultimate VA, which will be sum of VA of all three positive sequences. So VA1, VA2 and VA0. VA1 is for positive, VA2 is for negative and VA0 for zeroth sequence. Same way as you can find the VBs, we can find VBs based on alpha square VA1 plus alpha VA2 plus VA0, and similar ways we can find value of VC alpha into VA1 plus alpha square VA2 plus VA0, and you can express it in the matrix form, which I did here. You can see VA, VB and VC, I expressed them in the matrix form: 1 1 1 alpha square alpha 1 and alpha alpha square 1, and then we have the voltage vector VA1 VA2 VA0. Then we will call this whole matrix of voltages as VS. The matrix with alphas, we will call it A, and the matrix with VA1 VA2 and VA0, we will call it VP. Now we can write the equation to find VS from equation which like this equation. So we can first what we can do, Vs will be equal to A inverse into Vp, right? We want to find the value of Vs, so you can find Vs from the equation A inverse into Vp, right? So now you have to find the value of A inverse. You already know the value of A, so what you will do, you will find the A inverse. So A inverse will be 1 by 3 1 alpha alpha square 1 alpha square alpha 1 1 1, and now you will substitute this A inverse here, and you will find the value of VA1 VA2 VB3, and whenever you find it, you will find it like this: VA1 will be 1 by 3 VA plus alpha VB plus alpha square VC. Same ways will be for VA2, 1 by 3 VA plus alpha square VB plus alpha VC, and for VA0 it will be 1 by 3 VA plus VB plus VC. So what does these three equations indicates to us? So they indicate us that they actually give us the relationship for obtaining original phasor from symmetrical components, and we can find the same transformation for any other values as well, because here I have did for voltages. You can do the same for current as well. So you can transform your current as well for any set of phasors, and that was your symmetrical component of unsymmetrical phasors. So I will wind up today's lecture here. If you have any doubts or any queries related to today's lecture or any previous lecture, feel free to mention them in the comment section below. If there are any feedbacks related to channel, all the feedbacks are welcome, so feel free to drop your feedbacks in the comment section below as well. I will be seeing you next time. Till then, thank you very much for listening, and take care of yourself. Take care of yourselves. Goodbye. See ya.